In this video tutorial, we will introduce the topics of solutions and solubility. So let's briefly review over a few topics from grade 9 chemistry. First, what is a solution? It is a homogeneous mixture, meaning it has one visible phase. It is uniform throughout. So when I look at salt water, for instance, I only see one phase. I cannot tell the difference between the water or the salt dissolved inside of it. With water and sand, however, I see two phases. I see the sand, I see the water. When you can definitely tell that it's a mixture, we call it a heterogeneous mixture. So homogeneous mixture, one visible phase, you can't tell the difference. Heterogeneous mixture, more than one visible phase, you can definitely tell the difference. The solvent and the solute. The solvent is typically the component in the greatest amount, while the solute is the component found in lesser amounts. So if you want to think of it this way, the solvent does the dissolving, while the solute is the one being dissolved. Solute become a solution. Now solutions are said to have a variable composition, meaning they can have different solvent to solute ratios. As such, they can have different concentrations. Now just by looking at this diagram, I can tell that this darker colored solution has more solute. In such cases, we say that it is concentrated. Meanwhile, the lighter colored solution has less solute. In these cases, we call it dilute. Now if you recall, when we're dissolving or mixing something, this is a physical change. So the chemical composition remains the same, even if the substance looks different. Now because it's a physical change, these mixtures can typically be separated based on their physical properties. So here I have a mechanical mixture of water and oil. This is a heterogeneous mixture because I can tell the different phases. And I can separate the two using something called a separatory funnel. This device allows you to separate these compounds based on their density. Being less dense, oil floats on top, while water sinks to the bottom. So I can open up this valve and allow the water to drain out, and when the oil phase starts to show up over here, I can shut it off, thereby separating the oil from the water. When it comes to mechanical mixtures like insoluble solids and a liquid, I can use a filter paper. This will allow liquids that have small particles to seep through, while the larger particles in a solid form stay behind in the filter paper. So separating by density, separating based on particle size, and over here separating based on boiling point. So different substances typically have different boiling points. So for instance, ethanol and water. While water boils at 100 degrees Celsius, ethanol boils at around 78. The ethanol will boil first. Once we reach 78 degrees Celsius, the thermometer reading will stop, as all the thermal energy is going into breaking the intermolecular forces between ethanol molecules. This results in a phase change as the ethanol goes from a liquid to a gas state. As the ethanol vaporizes, its gases will come into contact with the cold glass at the top over here. When gas particles lose energy and cool down, they go from a gas state to back to a liquid state. So it's condensing. That's why we call this a condenser. Now this one's a fancy condenser because it allows you to plug in a tube here and a tube here, allowing water to come in, cool down the condenser even further, and get flushed out this end. The water and the alcohol never come in contact with each other because the condenser is double-walled, allowing the alcohol to flow through the inner tube, allowing water to flow through here, and coming out here, without actually coming in contact with the alcohol itself. This liquid cooling of the alcohol does a much better job of condensing it than the old-fashioned method of just putting cold paper towels over top of it, and then having to replace those towels when they dry out. Eventually, when the alcohol is boiled off, the temperature on the thermometer will start to rise again until it hits 100 degrees Celsius, and that's when the water then starts to boil away. Now, it's a common misconception that students always think solutions are liquids. Though it is often the case, it is not the only option. So for instance, air is a gas-gas solution. I know there's nitrogen and oxygen gas inside of air, so it's not pure. But when I look at air, it is homogeneous throughout. It's got one uniform phase. I cannot tell the difference between oxygen and nitrogen gas. Now brass is an example of a solid solution. It is typically made up of zinc dissolved in copper. So when you look at a brass trumpet, it all looks the same. It's one visible phase, uniform throughout. You can't tell the zinc from the copper. Now soda water is an example of a gas liquid solution. Unless you shake this bottle or open the cap, you can't see the carbon dioxide gas dissolved inside of the water. So again, one visible phase, uniform throughout. When you look at wine or a beer or other alcoholic drinks, it's alcohol dissolved in water. Again, they typically look homogeneous, one visible phase, uniform throughout. you can't tell the difference between the water and the alcohol, at least not just by looking at it. And now finally, the most common form most people think of when they think of solutions, solid, dissolved, and liquid. So salt water, for example. Once dissolved, it's one visible phase, uniform throughout. You can't see the salt from the water. Now, as in this case, water is quite often used as a solvent, a component that is in the greatest amount. As such, water is often referred to as the universal solvent, because we use it to dissolve more substances than any other liquid. So important are solutions that use water as a solvent, we give it its own state of matter, and we call it aqueous. So any solution where water acts as a solvent is said to be aqueous. Now take a look at these terms down here. Oil and water are said to be immiscible, while alcohol and water are said to be miscible. So based on these sentences, you can probably guess that immiscible means they don't mix, while miscible means they do mix. But now take a look at these two statements. Salt is soluble in water, while sand is insoluble in water. Again, just by reading the statement, you can tell that soluble means they mix well, while insoluble means they don't mix well. So here we have two terms, soluble and miscible, and they both mean that things mix well. Then we have immiscible and insoluble, and they both mean don't mix well. So what's the difference? When would I use one term over the other? Well, if you'll notice, oil and water are in the same state. They're both liquids. Alcohol and water, they're both in the same state. Liquids. So if the solute and the solvent are in the same state, we use these terms. Miscible, for meaning they mix well, and immiscible, meaning they don't mix well. Meanwhile, salt and water are two different states. Salt is typically a solid, while water is a liquid. Sand is definitely a solid, and water is definitely a liquid. So when you have two different states trying to mix together, we use the terms soluble and insoluble. So soluble means they dissolve well, insoluble means they don't dissolve well. So make sure you know when to use one or the other. Same state of matter, use these two terms. Different states of matter, use these two terms. Now, solubility quantitatively describes how well a solute dissolves within a solvent at a certain temperature. It's important that you mention temperature because if you change the temperature, you change how well something dissolves. You change its solubility. So for instance, I can dissolve more sugar in hot water than I can in cold water. I do need to factor in temperature. Now, if the temperature is not mentioned, by convention, we typically assume that it's at room temperature, 25 degrees Celsius. So if someone asks what is the solubility of salt, I would say 36 grams per 100 mils at 20 degrees Celsius. So 36 grams of salt can dissolve into 100 milliliters of water at 20 degrees Celsius. Now it's important to note that just because something is considered to be insoluble doesn't mean that nothing dissolves. It just means very little of it dissolves, typically less than 0.1 grams in 100 milliliters of solvent. So if I had 100 milliliters of water and less than 0.1 grams of the solute dissolved, we would say it's insoluble, even if some of it dissolved. The problem is the amount that dissolved is so small, it's negligible. We might as well say, didn't really dissolve, insoluble. Now, if something dissolves very well, say more than 1 gram in 100 milliliters of solvent, we say that it is soluble, while anything in between 0.1 grams to 1 gram is considered to be slightly or sparingly soluble. Now, as I mentioned before, the solubility of salt, table salt, at 20 degrees Celsius is 36 grams per 100 mils. So in a 100 milliliter beaker, if I dump 36 grams of salt, all of it should dissolve. But in this case, I'm only dissolving 30 grams, even though I can dissolve 36. In such instances, we say the solution is unsaturated, meaning it still has room to dissolve more solute. In this case, it can dissolve 6 more grams. But in this example down here, I'm trying to dissolve 40 grams of sodium chloride in 100 milliliters of water. Because I can only hold 36, there will be 4 grams of salt still sitting at the bottom, left undissolved. In this case, we say the solution is saturated. It can no longer hold any more solute. If you try to add any more, it will just sit there at the bottom as a solid. It will not dissolve any further. Now, there's one last state called supersaturation. This occurs when a solution contains more solute than can be dissolved by the solvent under normal conditions. Now, I only know of one example of supersaturation, and that is sodium acetate trihydrate. Under the right conditions, you can dissolve more solute in very little water, forcing them all to dissolve with no powder residue left over. But this supersaturated solution is extremely unstable at that point. So here we have some supersaturated sodium acetate trihydrate. It is not supposed to be in an aqueous form right now. It's been supersaturated. There should be a lot of powder sitting at the bottom undissolved. As I mentioned earlier, I can dissolve more sugar in hot water than cold water, and that's what we do over here. We increase the temperature of the water so it could dissolve a lot more sodium acetate trihydrate. But the key here is to let this solution cool down very, very, very slowly. This allows the water and the sodium acetate to form a structure that is very delicate but still in its liquid state. However, all it takes is one crystal of sodium acetate to fall down, and suddenly this delicate structure collapses and becomes a solid because there's just way too much solute and not enough solvent to dissolve it. So watch as they drop a crystal. You can barely see it. We call it a seed crystal at that point, a nucleation site, where essentially you'll start to see a domino effect, where that one small crystal destabilizes the entire structure, and you can see the solute recrystallizing out of solution. Alright, now the ability of a solvent to dissolve a solute depends on the force of attraction between compounds. Now this next part should be a review for us for the most part because we covered this back in Unit 1. But here we go. If the solute-solute attraction, so the attraction between solute particles, is greater than the solute-solvent attraction, so the attraction between water molecules trying to pull it apart, then we say the compound is insoluble. It won't dissolve well. If, on the other hand, the solute-solute attraction, so that's what holds the solid together, is weaker than the solute-solvent attraction, water again trying to pull it apart, we say the compound is soluble, so it dissolves well. Notice that ionic compounds dissociate into ions. So when we use the term dissociates, we mean that they dissolve inside the form of the unit. So the individual ions are being separated, ion by ion by ion by ion. Covalent molecules, on the other hand, do not dissociate into their ions. Because they're bonded covalently, we can't rip them apart atom by atom by atom because they're sharing electrons for stability. Whereas with ionic compounds, this cation no longer needs this anion. The cation has donates electrons to the anion is stable, cation is stable, they don't need each other anymore, so we can separate them. But again, these guys need to be next to each other because they're sharing electrons for stability. So with sugar molecules, for instance, we must remove the entire sugar molecule as a unit rather than rip them apart piece by piece. So the water molecules surround the entire sugar molecule. So in other words, they dissolve outside the molecular formula, so it's the intermolecular forces that are being disrupted. As I mentioned previously, when we talk about solubility, we must also mention the temperature, because temperature can affect solubility. We all know that sugar dissolves a lot better in hot water than cold water, so when it comes to solids dissolving in liquids, a higher temperature will typically increase the solubility, allowing you to dissolve more solids in that liquid. This is because the solute particles now have more energy and move further apart, while the solvent particles also have more energy and collide with more force. The solvent particles are better able to disrupt the solute-solute attraction in this case. Now with liquid-liquid solutions, like alcohol mixing with water, higher temperatures have very little effect on the solubility. Unlike solid particles that are very, very close together, liquid particles are already quite far apart from each other. So increasing their temperature provides very little increase in particle distances. Finally, when it comes to gases in liquids, so for instance carbon dioxide in water, higher temperatures will actually decrease the solubility of a gas in a liquid. I'm sure you've all tasted cold Coke versus hot Coke at some point in your lives. When you do so, you'll notice that there's a difference in their taste. The cold Coke tends to have more bite to it, while the warm Coke is just bleh. That's because gas particles already have a lot of energy and space between them. By providing these gas particles with more energy, it encourages them to escape the liquid phase. And so you have more CO2 dissolved in cold Coke than you do in hot Coke. Without that carbon dioxide, the Coke tastes flat. There's no bite to it. This is why global warming is such a problem for marine life. As the water temperatures rise, less gas can be dissolved in the water. Gases like oxygen, for instance. And as the oxygen levels decrease in the waters, more aquatic creatures begin to suffocate. You can change how quickly a solute dissolves with these three factors. As we mentioned before, increasing the temperature helps the solute and solvent particles to move faster, thereby colliding more often and, of course, dissolving faster. But you can also agitate the mixture, so shaking and stirring it brings fresh solvent particles into contact with the undissolved solute particles, again dissolving faster. Finally, you can increase the surface area. So for instance, powdered sugar dissolves a lot faster than a cube of sugar. That's because decreasing the size of the particles exposes more solute for contact with solvent. So in addition to dissolving the outer portion when it was in its solid cube form, crushing it up allows you to dissolve the inner part as well. Finally, changing the pressure can have an effect on solubility as well. Not so much with the solid-liquid or liquid-liquid solutions, as their particles are already quite close together, change things much. As such, solids and liquids are considered to be incompressible because it has so little effect. Where you will see a big difference is with gas-liquid solutions. Because gas particles have so much space between them, you can still compress them, even to the point where they turn into a liquid state. So if you've ever shaken a propane tank before, it feels like there's a liquid inside. That's because the gaseous propane is under so much pressure that it's been compressed into a liquid state. But the moment you release that pressure, that propane doesn't come out as liquid, it comes out as a gas, in your barbecue hopefully. Same thing with carbonated drinks. Under high pressure, the carbon dioxide stays in solution. But the moment you open up the cap, the pressure decreases. With a decrease in pressure, you decrease solubility and the gas starts to escape. Now, when it comes to predicting solubility, there are many factors that affect it. As such, the only reliable way to determine whether a substance is soluble or insoluble is to verify experimentally. Do it yourself. Mix the two together and see how well they dissolve. However, certain molecular characteristics can be used to help us predict a compound's solubility. If you recall, dipoles are two oppositely charged ends that are separated by a short distance. So when we look at polar molecules, one end is partially negative while the other end is partially positive. We call this the dipole. Di meaning two, pole meaning ends, two ends. Now, there is an attraction between the dipole of one molecule and the dipole of another molecule. We call this a dipole-dipole attraction, which is a type of intermolecular force. Now, hydrogen bonding is an especially strong type of dipole-dipole attraction, and we typically see it when hydrogen is bonded to a very electronegative atom, such as oxygen, nitrogen, fluorine, or chlorine. So these four elements are extremely electronegative, really want to attract electrons towards them, but they're just not strong enough to completely rip off the electrons to make really positive, really negative charges. But it's close, and that's why we have very strong partial positives and very strong partial negatives, resulting in unusually strong dipole-dipole attractions. So remember, hydrogen bonding is not a real chemical bond, it's just a very strong type of dipole-dipole attraction. But remember, just because there's a hydrogen present doesn't mean it's hydrogen bonding. You need to have one of these four very strong electronegative elements to start it up. Now, due to these dipole-dipole attractions, molecular polarity has an effect upon solubility. So when you try to mix a polar molecule with another polar molecule, their opposite dipoles attract each other, allowing them to mix well. With nonpolar substances, they don't really have strong intermolecular forces, so nothing really attracts them together, but at the same time, there's not much interference either. So nonpolar molecules also mix well with other nonpolar molecules. But if you try to mix a polar molecule with a nonpolar molecule, you'll find they don't mix well. That's because the dipole-dipole attraction holds the polar molecules together, preventing the nonpolar molecules from breaking through. Meanwhile, the polar molecules are unable to diffuse into this area because then you'd have to drag all the other polar molecules with you, and the amount of energy required to pull all these guys through here is unreasonable. So quite often you hear the phrase like dissolves like. So polar and polar substances, they mix well. Nonpolar and nonpolar substances, they also mix well. So like dissolves like because they are alike. But polar and nonpolar substances, they are unlike each other. They don't mix well. Now the last factor we need to look at is ionic charge. Typically, if an ion has a large charge, it probably has a large ion-ion attraction. Thus, highly charged ionic compounds tend to be less soluble. So for instance, phosphates with a 3- charge, that's a lot of charge, they hold tightly together with other ions. And if they hold tightly together, they're less likely to be split apart or dissolved. Nitrates, on the other hand, have a 1- charge. This charge is not as large as the 3-. As such, nitrates are more easily separated, making them more soluble. Finally, the size of the ion also has an effect on solubility. If you recall, cations tend to be smaller than their neutral atoms. Because cations lose electrons to achieve stability, they tend to lose that outer valence shell. Once that outer valence shell disappears, they're much smaller. Anions, on the other hand, have the opposite effect. They are larger than their neutral atom. In order to become stable, nonmetals gain electrons to become anions, giving them that outer octet structure. Now, smaller ions tend to pack together more tightly than larger ions. With larger ions, there are bigger gaps between them, while smaller ions are able to fill in those gaps, making them more tightly packed together. When tightly packed together, the force of attraction between ions is larger, because now those ions are closer together. Like magnets, the closer they are, the stronger the attraction. As such, compounds with small ions tend to be less soluble because they're more tightly packed together, they have a strong attraction between them, it's harder for water to remove them from their crystallized structure. Now this is a solubility curve. It provides us with information regarding the solubility of a solute in a solvent over a range of temperatures. So for the majority of these compounds, as you increase the temperature, you can add more grams of the solute into 100 milliliters of water and have it dissolve. So for instance, potassium nitrate, KNO3, at 50 degrees Celsius is able to dissolve 80 grams of solute in 100 grams of water. Now, just so you know, the density of water is typically about 1 gram per milliliter, at least at room temperature anyway. It does change at higher and lower temperatures, but we're going to assume the change is negligible. So for this course, assume that 1 gram of water is about 1 milliliter of water as well. So when this says grams of solute per 100 grams of water, you can also say grams of solute per 100 milliliters of water. That would be acceptable in this course. Now let's say I have a saturated solution of potassium nitrate at 50 degrees Celsius. So if you recall, saturated means I cannot fit any more. So at 50 degrees Celsius, I can fit 80 grams in 100 milliliters of water. So if I have a saturated solution of KNO3, that means I have 80 grams in that 100 milliliters of water. Now, if I were to cool this water down to 40 degrees Celsius instead, well, how much powder will crystallize and come out of the solution? Because at 40 degrees Celsius, I can only hold 60 grams per 100 milliliters of water. Originally, I could hold 80, but now I can only hold 60. So that means 20 grams of potassium nitrate will come out of the solution as a solid because it can no longer hold that much solute at this lower temperature. Now, on a test, you may be asked, now some questions may require you to gather data from a chart in order to solve the question. So let's take a look at this example. You wish to produce 250 milliliters of a saturated potassium nitrate solution at 50 degrees Celsius. So looking back at the chart, 50 degrees Celsius, potassium nitrate, I see that it can hold 80 grams per 100 milliliters, and that's the key here. It holds 80 grams for every 100 milliliters. So remember, even though it says 100 grams of water, I can also say 100 milliliters of water, because in this course, 1 gram of water is the same as 1 milliliter of water, but only for water. If this was oil or alcohol, you would not be able to do this. They would have different densities, so different ratio of mass to volume. So remember, only with water. Now, back to this. It says per 100 milliliters of water. But I'm not using 100 milliliters of water. I'm using 250 milliliters of water. So I need to convert this ratio to see how many grams of potassium nitrate can be dissolved in 250 mils of water instead. And when we solve, we find that 200 grams of potassium nitrate are in a saturated 250 ml solution at 50 degrees Celsius. So now that we have our starting information, it asks what mass of lead-2 nitrate and potassium iodide are required to react and produce this. So I'm going to write out this equation, lead-2 nitrate, potassium iodide. This is a double displacement pattern, giving me PbI2 and KNO3. Now don't forget to balance the equation. We always balance the equation, and this will give us our stoichiometric ratios. Now from the chart, I found that I have 200 grams of KNO3 required, and it wants to know how much lead-2 nitrate and potassium iodide are required to create this. So 200 grams of KNO3 and how many grams of Ki and PbNO3 will make this. So first step, convert to moles. Mole is equal to mass divided by molar mass. We got the mass, we got the molar mass of KNO3, and now we have 1.98 moles of KNO3. I then use my ratios, 2 to 2 between KNO3 to Ki, and I get 1.98 moles. 2 to 1 between KNO3 and PbNO3, and I'll get 0.99 moles. I then convert them back into a mass, because mass is equal to moles times molar mass. Molar mass of Ki, 166. Molar mass of PbNO3, 331.2. This gives me a final mass of 327.88 grams. Lead-2 nitrate is required to create 200 grams of potassium nitrate, but only if you can mix it with 328.68 grams of potassium iodide. Now, some students may ask, do I have to worry about limiting reagents here? The answer is no. You don't have to worry about who runs out first because neither of them runs out first. In order to make 200 grams, I've planned exactly how much I need of this and exactly how much I need of this so they both equally get used up at the same time. Alright, so our next topic is going to be on solution concentrations and dilutions.